So this is going to be lesson 8.8, magnetic fields. So here you see a bar magnet, uh, and you can kind of think of magnetic fields as similar to electric fields. They're not the same, but they are intertwined. So the magnetic field here, the magnetic field here, the magnetic field lines, the arrows always point towards the south pole, and the arrows always points out from the north pole, right? Just like electric fields, the arrows always point out from the positive and in towards the negative. Here, here you're going to point towards the south and out from the north. And opposite poles are going to attract, uh, and the same poles are going to repel. And this is really similar to electric charges. Now I want to kind of focus on the image on the top right. So you'll see here that the electric magnetic field strength. The closer the lines are to each other, the stronger the magnetic field. And you'll see that the lines kind of bunch up more the closer you are to the poles of a bar magnet. Right? So you see the distance between the lines here is much closer than the distance between the lines that are being circled. So let me kind of highlight it for you, right? So here, the distance between each of these magnetic field lines is much closer. That means the magnetic field strength there is much stronger than the further away you are, which kind of makes sense, right? You're stronger when you're closer. And if you guys ever tried dropping iron filings when we did this in class, if you were not here for that, right? If you ever drop iron filings around the bar magnet, you'll see that they kind of take that shape, right? They take the shape of the bar magnet itself. So, and then these magnetic field lines, they are real. It's exhibited. While you can't see it, it is there, right? So, any metal really, for example, iron filings, they kind of follow these lines. Again, this is an example of the magnetic field lines, again, between two like poles, right? So you have two north poles here. You can kind of see the curves, the curvature of these lines kind of bend away, right? And if they're the same, if they're opposite poles, well, the curvature of the lines kind of go towards and curve towards one another. Now, the cause of magnetism is not something you need to know, right? You're not getting tested on it. The regents will test you on it either. But the cause of magnetism is from electron spin. How they spin determines determines whether or not the object is a magnet or not. If you have enough electrons spinning in one direction, you cause the object now have a south and north pole. And the fun fact here is that, well, if you cut this bar magnet in half, well, you're not getting rid of the poles, you're just making two new bar magnets. And while the strength of the bar magnet itself will be weaker, you are still having two. You turned one bar magnet into two bar magnets. And that's because, again, the electrons spin a certain way, and just because you cut the object doesn't mean you disrupt the spin. Again, that's not really something you need to know. But you do need to know how to do this. So I want you to draw three magnetic field lines in the region between the magnets. And so because the arrows always point towards the south region, right, because it's attracted, the lines are going to curve here, right? I'm going to draw more than three lines. I'm actually going to visualize the other bar magnet here, right, because again, the north is attracted to the south pole. So there's kind of the magnetic field lines kind of pointing inwards towards the south. Same thing here, pointing towards the south. All right. And so 3B is a little bit something different. 3B, I kind of flip the magnet around. So we have two north poles here. And what are two north poles going to do? They're going to repel each other, right? Again, the arrows point outward. But again, they kind of curve towards the south pole because again, north and south poles attract. And you'll see that my art here is not perfect, right? I'm not an artist. I hope you guys can draw better than me, all right? But then again, that's what the field lines kind of look like. take a look at 3C. What is the direction of the magnetic field at point P? Well, field lines always point inwards towards the South Pole, right? They always point inwards towards the South Pole. Now, if we kind of take the combination of the two, well, the combination of two of these lines would just be something like that. Right? And so that would be the direction of my magnetic field. We don't know what happens to P, right? We can say P is like is a North Pole magnet, and we wouldn't know whether or not it could be attracted, right? It could go towards the bar magnets, or it could be a South Pole and could go away. But we don't know, but we do know the direction of the magnetic field. Now let's talk about Earth's magnetic field. Now you'll see here that in the bar magnet, your compass, the red needle part, kind of points towards the South Pole, right? The needle points towards the South Pole, follows the line of the South Pole, and kind of is repelled by the North Pole, but is attracted to the South Pole. If we take a look at Earth, the reason why compasses point north is because the compass is attracted to the South Pole of Earth, right? We can say geographically the North Pole of Earth is the northern part, right? So that geographically that is the North Pole, is the northern pole of Earth, but magnetically the South Pole of Earth is actually at the top of Earth, is at the north of Earth. That's why the compass points north. The compass is attracted to the South Pole of Earth, and the South Pole of Earth is all the way at the top of Earth. And the North Pole of the magnetic North Pole of Earth is all the way at the bottom, where the South Pole is. Now, Earth's magnetic field is really important to humanity's survival, because without it, the solar wind from the sun would kind of blow away a lot of our atmosphere. It would kind of take away our water. It would eventually evaporate. It would, a lot of high energy particles would hit our atmosphere, and we would kind of suffer. We would definitely suffer. And that's one of the theories on why Mars doesn't no longer has water. It's because, well, and somewhere along the way, Mars lost its magnetic field. Well, if we wanted to sketch Earth's magnetic field, actually, I can use this right here. If I wanted to sketch Earth's magnetic field, well, they kind of go towards the South Pole, right? So they emanate from the North Pole and they go towards the South Pole of Earth, right? So I want to sketch the South Pole of Earth. Well, that's what you get. That's what you get. Or rather, sketch the magnetic field of Earth. All right, let's take a look at this. So let's take a look at how, and that's we're done with magnetic fields, right? So now let's look at the modern day use of magnetic fields. And so let's show field meter, show field. So this bar magnet has a magnetic field around it. And you'll see on the right hand side here, you'll see a coil, right? A wire, and with electrons. So those tiny balls are electrons, and you see a lamp. I want you guys to tell me, well, all right, I want you guys to observe, well, what happens when I turn this faucet and then this water starts making this bar magnet spin? Well, what happens when you make this bar magnet spin is that, well, now you see the lamp turn on. And you see the electrons kind of moving back and forth, back and forth, back and forth. Well, that's weird. That's spinning a bar magnet somehow generates electric current, somehow generates electricity, right? And so this is essentially what you should see. And this is one of the best modern day, or rather one of the best realizations ever, is that if we have an alternating magnetic field, if we have a changing magnetic field, we're gonna start generating an electric current in a wire. And this is called electromagnetic induction, right? Us just spinning this magnet around generates electricity. And if you think about it, that's how hydroelectric dams work, right? In these huge dams, actually, there's an image right here. In these huge dams, let's take a look at this. In these huge dams, you have these giant magnets, and when the water flows through these turbines, right, they spin these magnets and they start generating. They start generating electricity, start generating electric currents. And it's through this knowledge, this process that, well, we get all of our electricity from. That's how dams work. That's how hydroelectric dams work. That's where we get our energy. And without this realization, without this discovery, well, a lot would be lost. A lot of progress would be lost. And if an alternating magnetic field generates a current in a wire, then the opposite can also be true. Right? And the opposite can also be true, because if we have a current, if we, for example, we take this battery here and you have electrons running through this wire, if we kind of move it through this coil, we also start generating electricity, right? So this a moving current, actually, I don't want to show this one. A move Having current also generates a magnetic field. So you'll see here that I have no current to start with, but once I do start that current, I start giving myself, or rather getting, an electric field around this coil. So the opposite can also be true, right? If you have electricity, you also have a magnetic field. So, and then also, again, that's what you guys saw there, right? If we kind of move a circuit, if we kind of move a circuit through a coil, right? We move a wire through a magnetic field, we start generating electric current as well. And in essence, we say that in physics, we say that this produces a potential difference in the conductor. Do you necessarily need to understand what this means? No, we just need to remember that this is what happens. It generates a potential difference in the conductor when you move a wire perpendicular to the magnet. And when we get to 7a here, which particle will produce a magnetic field? Your particle has to be charged, right? It also has to be moving, right? Because electric current are essentially electrons, so that's a charged particle. It has to be moving, so a moving charged particle, the answer would be D. Again, if you have a current, you produce a magnetic field. A current are essentially moving charges, moving electrons, charged particles. So 7b says the diagram below represents a wire that is not part of a complete circuit, just above the poles of the two magnets. Moving the wire downward between the poles in the direction shown in the diagram below will do what? Again, really the only thing you guys need to remember is that moving a wire, a current carrying wire, between two poles, two bar magnets, will induce a potential difference between the ends of the wires. And that's pretty much it. All right? That's all you need to remember. Doing this induces a potential difference. Probably I explained it more in class as well. What's this? So that's a video you can watch on your own time. Okay then.
Earth itself